Welcome to this video lecture. This is the first lecture in a series of 3 on data analytics for personalized and optimal therapy. The first lecture is about data in modern medicine. Medicine has changed considerably in the last couple of decades, and the main reason is that we have now the ability to generate large amounts of very sophisticated data, which we weren't able to do until recently. And now with the availability of these large amounts of data, the ambitions of medicine have changed. Since what medicine now tries to do is to achieve what is called personalized or precision medicine. And what we mean by that is we want to use all these sophisticated modern data to design the right treatment for the right person at the right time. So treatments are going to be tailored to the characteristics of individual patients. And in terms of data analysis, this means that we have to do the following tasks. We will want to be able to predict clinical outcomes. And in stroke, for instance, that would be whether or not a patient recovers or relapses, or what would be the response to specific treatments, and on which timescales would we expect to see recovery. And we want to make these predictions from the data that we have on individual patients. And these will be clinical data, there could be genetic data, lifestyle data, or there could be data recorded from wearable sensors. And if we are able to do these things, then we can also compute the optimal therapy protocols that are tailored to the measurements and the characteristics of individuals. And this is not necessarily easy, because medical data pose all kinds of challenges. And the first is that the patterns that we try to detect when we do data analysis can be quite complex. Also in medicine, we often have imperfect or missing data. Medicine is a messy business. And there's a lot of diversity in the measured variables, which could range from imaging data to genomic data to measurements from the blood and so on. And it's not always obvious how you can integrate these quite different types of variables in a prediction. And finally, there's the curse of dimensionality. And with that, we mean that nowadays we can measure so many variables for a single individual. This could be millions if we think, for instance, about genetic information, that it becomes really hard to see the difference between accidental patterns and real patterns. And I will come back to that later. So, we have lots of data. And sometimes people speak about big data as a concept. It just means we have lots of data. Now this is not a new situation in science, because in high energy physics we've had big data for many decades. In the financial world we have very large data sets. It is just that in medicine this is a fairly recent thing. This is really something of the last couple of decades. And when you think about large data sets, it is really important to take a distinction between 2 types of large data sets. The first is that we have many patients for which we have calculated or for which we have collected these data. Now, if we have many patients, then yes, we can have large amounts of data, but there are no conceptual challenges. The challenges are only of a practical nature. We need, for instance, larger disks to store all these data. We need faster computers. We need more efficient algorithms to process the data. But on the other hand, if the big data is in the many variables that we have for each patient, then the situation is very different, because we have conceptual challenges. We have challenges that require new methods. Because if we can measure millions of things for an individual, it is very likely that we will find something that appears to show a pattern, but that is just a pattern by accident. For instance, if I throw a dice 10 times, if I do this often enough, at one point I will inevitably throw 10 sixes. That looks like a very specific pattern, but it is just fluke. Now the same happens when you measure millions of variables for a patient. In addition, when we have many variables and complex data, we have to start worrying about variability. And I mean variability across different hospitals, for instance, where they use slightly different machines, where they use slightly different protocols, where the ethnic composition of the patient is slightly different. And we have to worry about things like disease interactions. Now, how do we process such data if we have large amounts of data? And these days you will often hear artificial intelligence being mentioned as a solution to the problem of having many data points, many variables. And when artificial intelligence is discussed or written about, you often see fancy names and fancy pictures. You will hear deep learning, you will see images like these. And these images mean absolutely nothing. This is just marketing. You have to really understand what goes on. And what goes on is in principle relatively simple. And that is that in standard artificial intelligence methods that are used these days, we are talking about a simple machine, a relatively simple machine that has this form where you have many layers of simple processors, each computing features of the previous layer. And in machine learning, what you try to do on the basis of examples of questions and corresponding answers, you try to make very small changes to the wires in this type of machine in order to bring the answers that are being given by the machine closer, slowly, step by step, closer to the answers that you want. And these answers that you want are provided by human experts. So these machines will never answer a question to which a human expert would not know the answer. They will learn the answers that are given by experts, but once they've learned it, the hope is that they will also be able to answer new questions and that they will be able to do it much faster than humans can. So suitable tasks for this type of machine in artificial intelligence are those where you have many data of the type question with a corresponding correct answer, and these answers are provided by humans. So the types of problems one should think of are, for instance, speech recognition, image analysis. The analysis of images in a clinical setting is a very nice application area for artificial intelligence. But in medicine, many tasks are not of this type. So I want to now show you why medical data can be tricky. And they can be tricky in a way that is impossible to capture by a black box machine like an artificial intelligence architecture that I showed you in the previous slide. And to give you a bit of feeling for this, let us consider a very simple scenario. I have a scenario where I have two hospitals, and both of these hospitals try to answer the following question. They have two drugs, drug A and drug B for a given disease. And they're asking themselves which of these drugs is the better drug. So what they do is they give drug A to a number of patients and they check how often this drug is having an effect, a beneficial effect. And they do the same for drug B. And in hospital A, they gave drug A to 100 patients, and let's say 40 of these benefited from the drug, which is a 40% success rate. They gave drug B to 500 patients, and of these 500, 150 were found to have benefit. And this gives you a success rate of 30%. So in hospital 1, the conclusion would be drug A is better than drug B because drug A has a better success rate. So far so good. Hospital 2 does the same, but hospital 2 has different patients. They have 200 patients to which they give treatment A. Of these, 36 had benefit of the drug, so that is 18%. They also gave treatment B, drug B, to 80 patients and found that 12 of these had benefit from the drug, so this is a rate of 15%. So although the overall success rates are lower, hospital 2 could be in a different catchment area, the conclusion would be similar, namely that drug A had a higher percentage of success than drug B. So far, there is nothing strange here. Both hospitals come to the same conclusion. They both conclude that treatment A is better than treatment B. Next, let us imagine that these two hospitals start working together. They start to collaborate on this question of finding out which is the better drug. So what they do is they pool their data. The first hospital had 100 patients that got treatment A, the second 200, so now put together there were 300 patients that received treatment A. Of these, if you add these two numbers, 40 and 36 of the two hospitals, 76 derived benefit. So that is a success rate, if you work it out, of about 25%. They do the same for treatment B. 500 plus 80, in total 580 patients receive treatment B. And of those 580, if you add up the two numbers of the two hospitals, you find that 162 had benefit, which is 28%. And now, all of a sudden, you notice something really strange. Namely, whereas initially, both in Hospital 1 and Hospital 2, treatment A had the higher success rate in percentages, if you combine the data of the two hospitals, you find that treatment B has a higher percentage success rate than treatment A. So this is apparently very strange, and it shows you how tricky it is in medicine, for instance, to combine data. Now, there is no trick involved here. I haven't done any cheats or sleight of hand. This is just a reality. If you add numbers up like this is what you find. And all of a sudden, it is no longer obvious that treatment A is better than treatment B. And if you dig a bit deeper, you will find that the explanation for this type of effect is that in Hospital 1 and Hospital 2, the likelihood that they gave a random patient treatment A versus treatment B are not the same. And these differences in local protocols in these two hospitals, they immediately cause this effect. But you see, this type of effect is not something that you can get a black box to deal with, because it involves thinking very carefully about what goes on. Another example is the example of missing data. I already mentioned that in medical data, it is quite regular to find that certain measurements were not available in a data set, and you never can find out why they were not available. And these are data, for instance, where that is the case. These are real data from a cancer trial. And what we see here is the fraction of people that survived up to a certain point in time, where time is measured in days. And you see different curves for those people who got a high dose of a given drug, the greens, and the red curve is the curve for people who got a low dose of the drug. So if you look at these curves, you see that the higher dose gives a survival benefit to these people. There are also patients for which the information was missing. So we don't know what happened to them, whether they got the high drug dose or the low drug dose. And naively, you could assume that they were missing this information at random. So they could be either from this group or from that group, which means that the curve for those people would be somewhat in between the red and the green. But if you actually look at the data and you plot this curve, you see something really different. You see that those people for which this information is missing had a really poor clinical outcome. They died considerably earlier. So the conclusion must be that in medical data, it can happen that the missingness of data is not random, but that information is missing in a way that is very important and that is predictive of clinical outcome. And if you use any naive method, any simple method to handle these missing data, for instance by taking an average over the two possible values that they could have had if they were missing, you will make dreadful mistakes. And again, this is something that you cannot handle with black box algorithms. A third example, again, related to the complexities of medical data. Increasingly, with populations that get older, we will find that even if we look at a given disease A, the patients that we will be studying have other diseases as well. It is rare for someone of advanced age to have only one disease. And the problem is that these diseases can act in a way that is not independent. And if that happens, you can get all kinds of very tricky situations when you look at data in a naive way. And I'm just giving you an example here. Again, these are real medical data. This is about the incidence of prostate cancer in Sweden. So we see here, plotted as a function of age, the incidence of prostate cancer for men that have never smoked in red, the red curve, the black curve refers to men that are still smoking, and the grey curve refers to men that have smoked in the past but that have at some point stopped smoking. Now, if you look at these data in a naive way, they would suggest that smoking protects you from getting prostate cancer to some extent because the smokers have a lower incidence than the non-smokers. And if you took this at face value, you would make dreadful mistakes. And if you look at it more carefully, you will find that it is not at all true that smoking prevents you to some extent from getting prostate cancer. This is a direct consequence of an interaction between lung cancer and prostate cancer. And this type of phenomenon happens increasingly when there are multiple diseases, multiple comorbidities that are not acting independently on patients. And you can see already that as a consequence of these things, you might well find that a treatment that looks beneficial is in fact harmful, or a treatment that looks harmful is in fact beneficial. And you may see things like what I show here, which is called false protectivity, which means that smoking seems to have a protective effect against prostate cancer, which is absolutely not true. But looking at it in a naive way would suggest this. And finally, I mentioned already that if you measure many things, you will sometimes see patterns that are simply fluke. And this is an example. There is a website, the link here, where someone has been collecting many data, and he was looking for data that happened to coincide or that happened to correlate. And this is an example. There are many more, where he plotted the age of Miss America over the different years in red, and in the same graph he also plotted the number of murders in the US by steam, hot vapors and hot objects in black. Now obviously they have nothing to do with each other. But if you calculate for these two curves a measure of the degree of similarity, which is called correlation, you will find a very high value. So this is the type of example that shows you be very careful when you measure many things, because inevitably you will at some point run into patterns, but these are not real patterns. They are fluke, just like throwing a dice 10 times and finding 10 sixes. It will inevitably happen at some point. And this is in medicine an increasing problem, because with the post-genome data sets that we have, we can measure millions of variables for a single individual. And one of these will by accident, or more of these will by accident, correlate with the medical outcome. But it is by accident, and it becomes very difficult to see the difference between real patterns and fluke patterns if we do this. And this phenomenon is called overfitting.